In every case, what appears here are the original columns, more or less as they first appeared. Even so, they remain current and include several conundrums still unsolved, such as whether the sum of irrational numbers pi and e is itself irrational. Almost every column also offers up problems for readers to solve and test their understanding, along with the answers for anyone easily frustrated. We hope that they will prove as inspirational to readers now as they did to earlier audiences. Kristen Ozelli, Book Editor. Section 1. Numbers real, imaginary, and in between. Seeing the integers through the trees. The simplest of all lattices in a plane, taking the word lattice in its crystallographic sense, is an array of points in square formation. This is often called the lattice of integers, because if we think of the plane as a Cartesian coordinate system, the lattice is merely the set of all points on the plane whose x and y coordinates are integers. The illustration titled The Infinite Orchard and the Points Visible from 0, 0 on the Lattice of Integers, found in the bonus material, shows a finite portion of this set, the 400 points whose coordinates range from 0 to 20. Think of the 0, 0 point as the southwest corner of a square orchard, fenced on its south and west sides, but infinite in its extension to the north and east. At each lattice point is a tree. If you stand at 0, 0 and peer into the orchard, some trees will be visible and others will be hidden behind closer trees. Here, of course, our analogy breaks down, because the trees must be taken as points, and we consider any tree visible to one eye at 0, 0 if a straight line from that point to the tree does not pass through another point. The colored dots mark all lattice points visible from 0, 0. The unmarked grid intersections represent points that are not visible. If we identify each point with a fraction formed by placing the point's y-coordinate over its x-coordinate, many interesting properties of the lattice, properties first called to my attention by Robert B. Ely of Philadelphia, begin to emerge. For example, each visible point is a fraction whose numerator and denominator are coprime. That is, they have no common factor other than 1, and therefore cannot be reduced to a simpler form. Each invisible point is a fraction that can be simplified, and each simplification corresponds to a point on the line connecting the fraction with 0, 0. Consider the point 6 over 9. Y equals 6, x equals 9. It is not visible from 0, 0 because it can be simplified to 2 over 3. Place a straight edge so that it joins 0, 0 and 6 over 9, and you will see that the visibility of 6 over 9 is blocked by the point at 2 over 3. All points along the diagonals that extend up and to the right from 0 over 1 and 1 over 0 are visible because no fraction whose numerator and denominator differ by 1 can be simplified. Note that many of the diagonals running the other way, from upper left to lower right, consist entirely of visible points except for their ends. All these diagonals, Ely points out, cut the coordinate axes at prime numbers. Every visible point along such a diagonal is a fraction formed by two numbers that sum to the prime indicated by the diagonal's ends. Two numbers that sum to a prime obviously must be coprime. If they had a common factor, then that factor would also evenly divide the sum. So such fractions cannot be simplified. Vertical and horizontal lines that cut an axis at a prime get progressively denser with visible lattice spots as the primes get larger, because such lines have invisible lattice points only where the other coordinate is a multiple of the prime. Is it possible to stand at 0, 0 and look into this infinite orchard along a line that will never, even when extended to infinity, intersect a tree? Yes. Not only is there an infinity of such lines, but also there are infinitely more of them than there are lines that hit trees. Consequently, if the direction for a line of sight is determined randomly,